Okay, so obviously this is a typo. So we are currently in lecture 11, not 12, 15. So it was my mistakes. Okay, so this is lecture 11, and I wanted to make this lecture quite short. Um, okay, let's try. Mm, so we are currently working with the source drain epithelial growth, and we know that that is done by selective epic growth. So the chemical reaction was already covered, and today we will talk about why we have such kind of anisotropy in this selective epithelial growth. But before doing that uh, lecture, so first of all, let me just announce two important modification in our Armstrong-Craft code. So some of you guys complain me about quite slow speed of Armstrong-Craft, and now we are at the middle of our exercise, so we have so many accumulated jobs, and when you change something at the last stage, then you must repeat all of already done jobs again and again. Say that you have spent already 2 hours for learning a simulation or emulation. After that, when you make mistakes, then you have to rerun them again and again. So that was the main point of a complaint. So I implemented a load capability of our previously generated CGNS file. So let's assume this case. So now you have a certain CGNS file. Its name is fin underscore inverter underscore fin.cgns. So as the name suggests, let's assume that it contains just a structure after fin formation. Now you have a fin, but you wanted to make dummy gates and spacer formation and spacer etching, blah blah blah. So that is your current interest. However, if you make any mistakes in your dummy gate drawing, then unfortunately you have to generate these fins again and again. So we can now skip this tedious job by loading the existing CGNS file. So let's assume that now you wanted to draw dummy gates and save the structure with a name of inverter underscore dummy gate .cgns, whatever. So you wanted to generate a new structure, and your execution is only for this dummy gate formulation instead of the entire procedure. So this is the way to load that CGNS file. So you can see that this is the exactly same as before, and we just set a new name. So this underscore dummy gate means that this should be your output, not your input, or to be loaded, the file to be loaded, and this is to be saved. So the file name at the end of dummy gate formation. Then where can you find the name of your initial structure to be loaded? In this case, inverter underscore fin.cgns. So just beneath of this craft statement, please add this load statement and just specify its name in this way. Then the file will be loaded. Of course, there is a restriction. So in order to generate this inverter underscore fin.cgns, you had to start from very beginning, craft something, and that has a certain specification of Lx and Ly and Lg in order to assign the size of your emulation domain. that should be kept as before. So because your inverter underscore fin.cgns contain assuming a certain size of your simulation domain, emulation domain, but if you just change it, so instead of that this let's say LZ becomes just suddenly 600, or it just becomes a half of it, 144, then what will happen? The indexing system assumed in your calculation is completely destroyed. So please do not make any change in this domain specification. So I said you can do it quite well. And also here you have a certain starting the initial one that should be also kept. So I have not made extensive test for this new capability, so there is no guarantee that that is really dummy proof. So if you make any silly mistakes, then also this code can be crashed. So but anyway, please try, and if you have any problem, please report to me, then I will try to fix them or let you know how can you avoid that problem. So from the user point of view, that is quite easy to use. Just add your final previous, the last structure, then start everything. Let's say that, for example, you have done already, for example, homework number 10. In order to perform homework number 10, you call your craft only once, and after that there are long lines of many lines of your emulation. So my suggestion is please divide this long line into multiple files, file 1, file 2, and file 3, whatever. So you can just set the number of your interest, and the only top part of your one is included in your first .cmd file. So of course you can change its name. After that, it is saved as 1.cgns. Then please load this 1.cgns and generate 2.cgns and send it to next level. Then you can make another and another. And let's say that you make some changes in your, for example, fin formation. Then what had to be done is do not alter this the original initial part. Only when fin formation part is related, please modify or start from only this modified fin formulation, then formation, then after that you can save a lot of time. So this is my suggestion to save your precious time. So please try to this one. So today's homework is quite simple. We do not have any further material for this homework. Just to repeat our previous homework number 10. But point is, in this time, instead of running one single long input file, so please divide. So division is of course your preference, and just to show me that, demonstrate your capability to make reasonable numbers of files and simulation lengths or time lengths. So that is my suggestion for you in this case. Another important announcement is, in order to correspond to increasing need for this Armstrong craft, I have changed internal behavior of our deposition and especially deposition code. So previously we were able to just name a certain reason if we wanted to make a certain reason. I mean that. So previously, let's say that there was a silicon, and now assume that you wanted to introduce, for example, the one called as dielectric. Then previous input file was just to say that depot and region equal to dielectric. Then automatically this region name was recognized, and you have a new region. Its name is dielectric. But in this newer version of our Ångström Craft, that is not a safe way to do that. So before calling any kind of new name, like dielectric in this case, please add one line. So this line is just to declare that there exists a certain region whose name is, in this case, not this one, dielectric. Then it will be just added a list of regions inside this code. So actually I did not intended to make this modification. So but I made modification in the code and found that without this region specification it doesn't work. So this the way instead of changing the code, I just let you know how can you avoid this kind of complication related to the newer version. So whenever you introduce a new region name, then please, before doing that, just assign this region, new region. So in this example, so let's just have a look at my own example. Let's assume that you wanted to introduce a new region whose name is silicon germanium. Actually, we will do this job very soon, maybe in next year or not next year, next lecture or second next lecture. And this silicon germanium is used for, especially for P MOSFET to make source and drain. In the case of N MOSFET, we do not use silicon germanium. We just use silicon slightly added phosphorus in many cases. You know, in many cases, when we make N plus doping, also when you use ion implantation to generate highly doped N plus region, we usually use arsenic atoms. So that was most of our choice. But in this case, in our FinFET source drain formation, usually we use phosphorus and add an alloy between silicon and phosphorus. I'm not saying that this is dopant, so this is a kind of a alloy with extremely low, how can I say, portion. So just orders of a certain percent. So our usual doping concentration is even smaller than 1% of a silicon atom. So that's the reason why we call doping as a doping or impurity. However, in this case, a portion of a phosphorus atom is beyond 1% of our silicon number, so it is not just treated as a simple doping or impurity. It should be regarded as in between perfect silicon crystal with certain amount of phosphorus atoms, but and also alloy between silicon and phosphorus. Well, anyway, so now you can understand we are now trying to make PMOS source drain formation, and without this one, let's say that I have not assigned this one, then I will, let's also assume I call this model, and model name is this one, and select because I wanted to grow our silicon germanium region on top of our silicon fin. Starting from silicon, we wanted to make a certain diamond which is made of silicon germanium. That's the reason why this model contains the select option for silicon. Starting from silicon, we will make one layer of silicon germanium. So at the initial step, we will have just a thickness one layer of silicon germanium. However, if we repeat once again next step, when we do not introduce this one, now this one is just a silicon germanium, not silicon. So it is not included in our model specification. That's the reason why we will have just an extremely thin layer of silicon, even though we try several times to make a thick and tall silicon germanium source drain regions. So this is needed. You must also include this region already existing silicon germanium. But point is, when you neglect this region assignment or declaration, then this name silicon germanium is not recognized by the Armstrong-Craft code. So that's the reason why this one becomes quite ineffective. So now let me just summarize. We have a model specification. This model specification is used to control the selective growth or sometimes etching of our materials. And it contains certain select options to turn on and turn off for our model selectivity, material selectivity, but without specifying its name in advance, it is not recognized. So we must add this region here. Then maybe you can ask me this question: should we call this region declaration just in front of model specification? Why don't you just call this region specification at the very initial point of our Craft code? Yes, it is also acceptable. So if you know all the list of your materials or your reasons, then just you can declare them all, then no problem about this problem, because the appearance order itself is not that important. Whether it was already declared or not, that is the only concern of this model specification. So are you with me? This is motivation of this important change. So I'm a little bit afraid that when you repeat our homework 10 in order to use this load capability, then maybe even though you have not changed anything, the behavior of our code, newer code, can be different from your previous one. So the reason why I give you this homework number 11 is just to test the correctness or compatibility of your new implementation or new exercise and your previous one, and you can show me that you can generate the previous result without any difficulty. So that is the reason why I give you homework number 11. So are you all with me? Okay, so then do you have any question about this homework number 11? So this is just nothing related with the physics or engineering, just code uses, but this is quite important for practical durability of your project. So if you don't have this load capability, then I cannot imagine how many hours you will spend for this simple structure generation. So that is practically very important. And do you have any question on this stuff? So if you don't, then let me just go to our main topic today. So I wanted to make it as short as possible. So previously, in previous lecture, we have shown that selective epigrowth is quite important to have a source and drain. But when we make a certain experiments using this chemistry, then we observe that there is a certain unwanted, usually unwanted phenomena called as facet. So this one shows typical or a certain surface aligned to certain atomic structure. So we have seen that also that is changing. Okay, maybe it's better just to yes. Why don't you just okay? So maybe you have seen it before. So let me just repeat it again. So it starts from our initial level. After that, we have grown a relatively thin layer, and in this case, we can find a relatively low angle surface, and it is labeled as 311. After that, if we grow it further, then we can find a more steeper surface here and relatively lower one, but its angle is even this one more moderate one is more steeper than this initial phase, and of course this one is corresponding to our wafer surface. So we will talk about why do we have this kind of behavior. Problem is this phenomena is a combination of many things. So let me just name them from my own understanding. So this problem is complicated because there are some factors. First one is related to gas. So you know we are using DCS gas and pour that gas into the chamber. After that, we wanted to hope that that chemical reaction happens. This DCS is decomposed into crystal phase silicon and also other kind of resultant gas phase. So that is the expected behavior of our chemical reaction. But point is, in order to make a uniform growth, we have to understand everywhere in this chamber we have a uniform distribution of this DCS one. But unfortunately, for example, let's think about this one. Now here we have certain fins, and let's say that there is also other fins, and now DCS gas comes in, and of course it is spread over all our wafer surface. But point is, here we have a wider opening, and this opening is quite narrow compared with a wider one. Okay, but at the initial stage of our fin formation, it's okay. Then let's wait for a while. Then what we will have is, now there occurs certain diamond, and also we will have a certain diamond. So sorry for my poor drawing, but anyway, we have a certain enlarged version of our silicon or silicon germanium. In this case, please think about the situation here and there. Previously, although it was narrow, but anyway we had a certain amount of opening, but now it becomes wider and wider. Eventually, if our source and drain growth is too fast or wait of too long time, then eventually this opening will become quite narrow. It means that the injection of our DCS gas into this void, not perfectly void but close to void, that part is really slowed down, and the concentration of DCS gas can be quite low. Then what will happen? In this case, since we have no DCS gas to be decomposed into silicon, so its growth will be limited. But in this case, wow, we have no limitation. So it really depends on the size of our system. So this is critically very important. So we have to understand the concentration of DCS gas. It means that we must consider propagation of DCS gas, whether this DCS gas can be found in this point or not. In that case, people are talking about ray tracing. Ray tracing means that this is ray is a light ray or gas ray, and sent from certain top point. This one, this vector just to describe motion of our gas, and it hits our wall. After that, is reflected and hit another fin and go to there and there to be eventually meet our wanted, desirable point for chemical reaction. This kind of ray tracing is required. That is quite an important issue nowadays, because in reality, our fins or nanosheets are nowadays so much densely populated. So although we just use the same recipe for this strain epi, we found some difficulties to make a desirable structure. But right now, we will not consider this effect. We assume that everything is just uniform. Wow, we have so uniformly distributed DCS gas, so reaction seems to be quite uniform. And another one is spatial boundary condition. So it means that we have, for example, 001 vapor surface. Then if we have an infinitely large surface without any hardware generated by, for example, silicon dioxide or silicon nitride, then what will happen? Or let's say that this length scale is too long, like several hundred micrometer, let's say. Then we are now trying to grow something. Then obviously there will be something strange due to this boundary condition. But at main body of our this opening, we will have just growth of 001 surface that is uniformly grown, and only the part related with this retarded interface will be delayed, so we will have this behavior. You can find such an argument here. This one, we have grown 240 nanometer growth, and you can see that here we have boundary generated from locus. This is oxide. So the growth of our silicon at this point is delayed. So that's the reason why we have a certain slope here. However, away from certain amount from this point, now you can see that this growth is just planar, and you can find just the expected behavior of our one-dimensional planarized growth of epitaxial. So let's come back. So boundary condition, boundary, shape of boundary, and where do we place boundary, that is quite important to predict the behavior of our one. And finally, we have also crystal property itself. So this is the one we will talk about right now. Why do we have different growth rate depending on surfaces that will be discussed here. So that is quite a difficult problem. So, and I'm saying that although I'm named these three effects, but each of them has more complicated one. So I just give you certain broad sketch on this issue. Anyway, please have a look at this specification. This is the typical one we have currently. So 001 vapor surface. So 001 means that actually corresponding to 100. Sometimes I will say 001 and sometimes I say 100, but when we have this curly bracket, so this is corresponding to a family or a set of vapor surfaces. I mean that 001, 010 and 100, they are all belonging to this curly bracket 100 surface. So now you understand. But in this case, I always say that the vertical direction is G direction. That's the reason why I'm using 001 here. But even in literature, research papers, they sometimes use, even in this case, they name it 100 without curly bracket, just a parenthesis. So they sometimes researchers are not that rigorous in their coordinate or notation. Please understand. But anyway, this is our conventional situation. So we have 001 vapor or 100 vapor surface, and channel direction is usually set as 110 direction. You must understand the difference between parenthesis and this bracket. So I hope that you are already be aware of this difference. So this parenthesis is used for a certain surface description, and this bracket is used for direction description. Of course, in this cubic system, they are actually equivalent to these numbers, but let's just make a difference notation, because generally it is the way we have to follow. 110 channel direction is the standard one, and I have seen through my research career, I have seen so many attempts to change directions, or I mean that sometimes they try to change vapor surface, sometimes they turn their channel direction. But as much as I understand, during my career, there was only one time success for rotating channel direction, only once, and that happens around 2000, starting from late 90 into the 2000. They succeeded only once. In this year IDM, you can find certain suggestion for once again rotating our channel direction from 110 to come back to 100 direction, only for certain type of devices. I'm not that sure about the fate of that attempt, because changing direction or changing vapor surface introduce a lot of problems. Please understand, although in this course we are just talking about some physics and some crystal structure, but hidden cause of difficulty of rotating something is always related with the issue called as reliability. I mean that this is not taken into account by the initial stage discussion, but actually this is the killing factor. It means that everything looks just okay. You have made with different channel directions. Wow, now let's use it. Yes, it shows also quite an acceptable amount of current, but it is found that if you use the new device long time, then actually suddenly it's dead. That is the problem of reliability. So even for silicon cases, this reliability is critically important. So that is the killing factor of many dreamers. There are many dreamers who say that, why don't you just introduce something? So at the initial phase, it looks okay, but we have to survive even after 10 years of using electronic devices. So that is critically important point. So every attempt was failed because due to the reliability problem. So I'm not quite sure there are new attempts for rotating. Of course, they have their good reasons. Why? Because now we are working with nanosheet transistor, and happen to be, in the case of a FinFET, this 110 channel direction was found to be quite a good choice for channel direction. It's good for mobility improvement. Everything was quite reasonable. However, when you come back to nanosheet transistor, even though we will discuss this issue again, but we have actually drastic change its major surface. So let me, please allow me draw a little bit. So now you are looking at our fin structure. Right now, this direction is, let me just draw direction. So this direction is corresponding to 001 direction. And this guy is corresponding to 110 direction. Yes, perfect. Now we have, in this case, if we have this surface on or this surface, let me just highlight them again, this one and this one, or the surface corresponding to this one and this one. Even though that is called as a tri-gate, but as you know, even in our ASAP7 case, this is just a 7 nanometer, and this is a 32, and this is a 32. And even more advanced devices, this length, fin width becomes even shorter, like a 5 nanometer, and height becomes even taller, 50, 60. So among, please select the more important surface. So you can easily understand when you make a comparison between these two surfaces, two types of surfaces, this guy and that guy, obviously from the viewpoint of its effective length, this one is far more important. So actually, although we had used this 110 wafer surface, but in the case of a FinFET technology, our surface is corresponding to kind of a 110 family. So we had used this wafer surface internally and also use this channel direction. But nowadays, although this is far beyond our current discussion, right now we are introducing a device structure called as a nanosheet. In this case, our structure just containing multiple stacks of this nanosheet. And when we take into account once again directions, then this is corresponding to 001, and this one is 110. So previously, it was the most important surface, but now most important surface becomes once again this guy. Yes, now we have this surface, and in this surface we have a severely different behavior between N MOSFET and P MOSFET. That introduces quite much difficulties. So let me just summarize this one. If you attend a certain course corresponding to digital design, then at the beginning of your digital design, the textbook says that, okay, N MOSFET and P MOSFET usually shows quite much difference of drivability, drive current, because electron has much higher mobility, but at the same time hole shows much lower mobility. So in order to compensate this mobility difference, we have to introduce a relatively wider P MOSFET. That was the usual lesson we found in digital integrated circuit course. But that was correct only for old time technology. In the case of FinFET, happened to be this kind of constellation, the amount of current observed in our FinFET technology seems to be almost close to 1:1. We don't have to yield to P MOSFET for balanced performance. That was FinFET case, and now we are coming back to our another direction. And when you go to nanosheet, then in this case, once again, unbalance between N MOSFET and P MOSFET becomes more severe. In this case, then why don't you just allow more wider channels for N MOSFET and P MOSFET? But that's not possible. You know that nowadays we have no room to any further allow wider devices. We are using the minimum size devices everywhere. So also the freedom to change it or freely change it to wider PMOS and narrower NMOS now is diminishing, because even when you have a look at FinFET fabrication procedure, everything just looks like a uniform. When you make a fin should be placed uniformly, and when you generate dummy gates should be placed quite uniformly. So it is very difficult to effectively change the width of your standard cell, because when you increase somewhere, then there will be certain wasted silicon areas somewhere in your standard cell. So let's just come back. So anyway, this is the mostly widely used standard configuration of our electronic devices. We have a 001 wafer surface, and channel direction is 110. So I have prepared one coordinate system shown here, and it shows the current situation. Here we have a wafer normal surface 110 direction, 001 direction, and in this figure, this horizontal direction is channel direction, 110 direction. Then, although it is drawn here, but this is right angle. Oh no, not right angle. This is 45 degree, and this is 45 degree, and we are just here. We are just drawing the surface or plane generated by this 001 and 110. We are just observing this one. This is the one corresponding to our TM images. when we make a TM image, we are now looking at this one. Then here we have some balls, and blue balls and red balls. They are all silicon atoms. So why I have introduced why I distinguish these two, just for your visibility. They are equivalent silicon atoms, and a pair of these two balls makes the basis of our diamond structure. Okay, so then now think about what is the surface corresponding to one direction when we read or when you watch the TM image. If we just have some resolution to watch or see atoms, then if that is bulk silicon, then we will have these dots. Everything will be seen as a dot, and when we introduce this one directional unit vector, this is corresponding to our 1 unit vector, and you can see it has certain angle from our wafer surface. When you calculate this angle, then you can find that this is corresponding to 30.3 degree. But actually what we see is not this normal vector. We see this surface. So since this is 35, so the angle between our surface 1 surface and our wafer surface, this angle becomes 54.7 degree. This is the number I have already explained in our previous lecture. I told you that we have a diamond, and the reason why we have a diamond is our 1 surface shows certain angle with respect to our wafer surface, and this is slightly higher than 50 degree, and this is the correct number for 1 direction. So simply speaking, the diamond structure we are observing, especially in silicon germanium epi layer, is corresponding to just 1 surface, and you can see it here. This is corresponding to our 1 surface, and this angle is 54.7 degree. Then the reason why I'm talking about this one is not just showing this 1 direction. We have initially other direction. So can you see it clearly? So at the initial point we have lower angle growth here. This one shows a much moderate increase, and people say that this is corresponding to 3 surface. So just to following the same procedure, please try to identify the 113 direction. When you draw 113 direction, this is the direction for 113, and of course our surface 113 surface is normal to this direction, and you can find this is the direction for or surface for 113, and when you calculate it, then this angle is just 25.3, so much smaller than our previous 111 surface. So it becomes dominating at the initial point, but later it is catched up by our 111 surface, and it's gone. So now you understand, at least, although we have not discussed many details about it, but when we have just to look at TM images, virtual TM images, then you can find that depending on surface, we have different angles. So now let's say why we have different growth rate for our two different dominant wafer surfaces. So of course our discussion is assuming that there is a reference one. What is the reference one? The reference one is 0, 0, 1. This is the dominant one, the reference one, and compared with this one, we have different numbers. So fortunately, in this paper, we were able to some experimental result. So this one, let me just draw. This blue line is corresponding to the initial stage before selective epi growth, and intentionally they introduce a certain point corresponding to silicon dioxide. So here the growth of our silicon is more or less limited, and instead in this bulk part now we have a fully planar growth of our 100, but anyway 100 surface growth. So let's say that this is the reference one, okay, and this is what we wanted to have. However, nearby this boundary we have a different thickness, so they just measure the thickness normal from this observed. They have the TM image and take this difference, and they say that this is corresponding to more or less corresponding to the growth rate because they are grown at the same time. And when you have a look at this thickness, of course depending on growth temperature, the ratio change. But please understand, here we have 0.6, 0.8, and here we have 1.0. And 1.0, what is 1.0 in this case? This is corresponding to our 100 surface. Always 100 surface is the fast one, and other ones like 110, yes, this one shows much slower growth rate. Then maybe you can ask me this question. Yes, let me just accept it. 100 grows faster and 110 grows slower. Then why do we have 111 surface instead of 100 surface? Fastly growing one should dominate. That is our initial naive thought. But please think about this one. When we have, for example, when we have a certain circular shape as an initial one, it can contain a lot of different surfaces. And let's say that for certain direction, for example, this direction, we are quite fast. Then we will have a movement of this initial surface into that way. And let's say that for this 45 degree, let's assume that we have a very slow growth rate. So instead of this large amount, let's say that it goes only in this way. And in between, we assume that moderate or smooth interpolation. Then what will happen? In this case, although it was a circular shape at the beginning, but later we will find that the shape looks like this, because this part is now, because it is slow, this slow surface later becomes dominant one. This is, at least to me, when I first saw this sentence, I a little bit confused, because I thought that first one will eventually determine the shape, but in this case, the slowest one determines the shape of our final structure. So that's the reason why 110 is the slowest, and that's the reason why we have the diamond shape determined by 111 surface instead of 100 surface. The natural question is, then why do we have slower speed for 111 compared with 100? Is there any reasonable way to explain it? So I'm not that expert on this aspect, but also I just dig out literatures, and my understanding is like this. This figure just shows 001 vapor surface, and here we have once again blue dots and red dots. Yes, they are also all equivalent silicon atoms, but in this case blue atoms are corresponding to the top layer of our 001 vapor surface. So second layer, just beneath of this blue layer, these atoms are represented with red dots. So now you can understand there is a certain okay, so please try to imagine, and if you cannot get it right now, then please do your own exercise, mental exercise. Now we have top layer corresponding to blue one. So although this graph is just obtained by projection, so this red one and blue one are projected along this g direction. They are shown equivalently, but please note that this is just blue ones are found at the top surface, and this one is slightly behind or below this blue one. Red ones find a little bit deep in our vapor surface. And now think about the perfect surface. Now we have blue dots, a plane of blue dots, and just beneath of it we have planes of red dots. And now we wanted to the next level of our silicon atom, because we wanted to grow a new layer. Then where is the position, right position for our new layer? And that this one is corresponding to the new position for our next atom. So if we introduce this next atom, although they are all projected into the same plane, so this is, if this height is 0 and this, if this height is -1, then this height becomes a positive 1. So this is basement, and this is ground level, and this is first floor. So then question is, how many nearest neighbors are found in this yellow atom? Nearest neighbor means that just the closest one you can find, and answer is quite clear. These two are nearest neighbor to this newly added atom. Yes, that's the reason why I'm saying that there are two nearest neighbor atoms in this newly added atom. And how about second nearest neighbor? So second nearest neighbors are found, they are found, which color will be best for? You can find that these four will be our second nearest neighbor. So it means that once a silicon atom just placed one place on the completely flat surface, then it can fill two nearest atom and four second nearest atom connected to this new atom. So that is a situation for our perfect 001 vapor surface. Then now let's go to our 111 wafer surface. I'm just saying the same thing. This blue one is corresponding to the top surface of our 111 surface. And this red one is just beneath it. So they are quite shallow because the distance between this blue and red should be equivalent in every case. In this 111 case and this 100 case, here you can find the stick connecting two blue and red dots, and their lengths are the same. It means that here, actually, although it is projected, this length should be equal to the length shown here. It means that the distance between them are quite vertical distance is quite short. In this case, please try to add one more atom. So on top of a perfect 111 wafer surface, try to add one atom. Where will be the right position for this new atom? So here we have a blue one. Yes, for example, let's think about this one. This blue one already connected to this red one, and red one. And they should make the fourth one should generate a perfect tetrahedron. And this blue one is at the body center of this tetrahedron, and we have three vertices of a tetrahedron as a red dot. And our new one should place just on top of this blue one to eventually get perfect tetrahedron. So please, I fully understand you cannot imagine right now. So I also failed. So although I'm talking in this lecture, I tried many times just to rotate my balls and sticks and saying this one. So it means that if we add one additional atom, that should be just on top of our blue dot. So please think about, once again, nearest neighbors. How many the first nearest neighbors for these yellow dots? So yellow dot will see only, or if we add something here, then it will see only one blue dot. And if we go to second nearest neighbor, we will see only this red one, and this red one, and this red one. That will be the second nearest neighbor. So simply speaking, there is only one nearest atom for 111 surface, and there is 3 second nearest neighbor atoms. Why it is so important? Because it means that if we add one atom on top of a perfect 100 surface and 111 surface, the one placed in this 111 surface have less number or smaller number of neighbors. Once it is attached, then in this case, if this is corresponding to 100 surface, then there are certain connections to keep it quite safe. And if we have a 111 surface, well, now we have a much weaker connection, atomic bonding, to keep it safe. So simply speaking, the reasoning why we have a higher growth rate for 111 surface instead of 100 surface instead of 111 surface is the strength of bonding between newly added atom and existing silicon atoms. So since this 111 surface has a stronger bonding, So once it is added, usually it is not escaping. But in the case of this 111 case, although it is placed, but it has a higher probability to escape from this placed position. So although the incoming is the same, but let's say that it doesn't escape and it escaped. Then what is the net growth rate? It is obvious that this one will have this amount of growth rate, and this one will have much lower growth rate. This is the usual way we explain why we have different growth rate for 100 and 111 surface. Simply speaking, depending on surface, we have different atomic configuration and different number of nearest neighbors. So these differences in nearest neighbors, first one and second one, or even third one, that introduces certain differences in growth rate. Okay, so this is just a physical description, and I hope that I deliver at least a sketch on why we have anisotropy, and in the next lecture we will talk about how can you then consider this anisotropy in our modeling tool. But as I told you before, since we are just using just a voxel based implementation, it's very difficult to consider the perfect diamond steps, especially even for commercial ones. This generating the shape of a diamond shape is regarded as very difficult jobs, and in many cases they just draw diamond step. But I don't want to do that. So although that is not perfect diamond one, but we will try to mimic the shape of a diamond one as much as possible, and understanding the limitation, we will keep our exercise. Okay, so let me wrap up today's lecture. Lecture 11, homework 11 is just to repeat our previous homework, but since we have changed our Ångström-Craft code, then please redo it and convince yourself that I can do it now much faster than previous cases. And that was all for lecture 11. And do you have any question? No? Then I will wrap up today's lecture. Thank you.